So in this lecture, we're going to explore a different way of adjusting the accelerator. We're going to explore what happens when we change the beam current that's going through the accelerator. In the past lectures, we adjusted the RF power going to the accelerator by adjusting either the RF driver power to the klystron or the klystron pulse voltage. And this, of course, changes the electron beam energy because the energy gain of the electrons in the accelerator is dependent on the amount of RF power that's going into the accelerator. However, we also know that if we change the number of electrons, the quantity of electrons that enter the accelerator, this will also change the electron energy because now the amount the available power from the RF beam coming to the accelerator has to be shared between different amounts of electrons, which will affect their energy. So what I've done here is I've reset our 15 MV beam. So we've reset the base parameters: 67 watts for the RF driver, 125 kilovolts for the klystron voltage, and 155 amps for the bending magnet. And I'm going to leave those the same. And now I'm going to change the gun voltage, which will change the amount of current that's going into the accelerator. So so the 15 MV beam is set with a 10 kilovoltage gun pulse. What I'm going to do is I'm going to drop this now to 7 kilovolts. And what's going to happen is with 7 kilovolts, we're going to have a reduced amount of electrons entering the accelerator. And so in this case, because of that, the beam energy that is exiting the accelerator is going to increase. We had 14.73 MeV before. But now, because we have fewer electrons that are now entering the accelerator, we had over 200 milliamps before. Now we've dropped that to 123. That beam current now has the same amount of RF power entering the accelerator, so there's the same amount of energy, but because there are fewer electrons, these electrons can be accelerated to a higher energy, 15.4 MeV, which then exit the accelerator. But now, because we haven't changed the bending magnet, what's happened is that still the bending magnet is only letting 15 MeV electrons go through, and so the target current has dropped to 3.46 milliamps, which has given us a drop in dose rate. So we can explore what happens if I now adjust this. So I'm going to adjust the gun voltage now, say up to 8 volts. So now we're going to have more electrons going through the accelerator. So we have a higher gun current. We have we now have a lower beam energy because those electrons have to have the same amount of RF power accelerating them, and our dose rate increases. So again, we can sweep this up again. So if we can go from 8 to 9 kV in the gun, we have more current. Energy drops. Now we have a 14.9 MeV beam coming from the accelerator, which is very close to the 15 MeV beam that the bending magnet is allowing through. 6.78 milliamps of current striking the target, producing a dose rate of 323 centigrade per minute. If we can keep on increasing now, we go to 10 kV. We're going to have a higher dose current. So now we have a 211 milliamps. We have a 14.73 again, producing a beam current of 7.23 milliamps, and we have a higher dose rate still, 345. I'm going to increase this now to 11 kV. So now our dose rate is beginning to drop off because our beam energy now has dropped to the point where we've beam loaded the energy down to 14.5 MeV, which is now lower than what the bending magnet is allowing through, and further increases in the gun voltage are going to lead to lower energies, which will lead to a lower dose rate. So now we have 14.2 MeV. Dose rate is now dropped to 184. If I go to 13, we now drop off to 81, which is the lowest dose rate. So what I can do again, as before, if we wanted to, we can now recover the dose rate by adjusting the bending magnet current. Now, we normally wouldn't do this on a clinical accelerator because we don't want to adjust the bending magnet current because that's what sets our beam energy on the target. But just for the purpose of the example, and because this is a simulator and not a real accelerator, we can do this without worrying about damaging anything. So now, just to show, so I'm going to now decrease the bending magnet current, and by decreasing this now, say to 100, and say we'll start with 150. Our dose rate has increased quite a bit. I can probably decrease this even further. Let's go to 145. Now we're going to get dose rate of 455. Let's go even further. So we go to 140. Dose rate now drops off again. So I've gone too far now because now the bending magnet is allowing energies that are going through that are higher than what the accelerator energy is. And so in order to get the highest dose rate, I'd have to adjust the bending magnet current to allow the equal energy of electrons from the accelerator going to the target. I can do the same thing again if I'll go back to 155, which is where we started. And then what I'll also do is I'll just reduce the gun voltage down to 7 kV just to do a similar exercise at the low end of the gun where we have the lower beam current, so the higher energy, because now we have a lower beam current here producing a higher energy. Now in this case we're going to have to increase the energy of the current in the bending magnet in order to match the electron energy from the accelerator 15.4 exiting the accelerator, and the bending magnet is only allowing 15 through. So if I increase this now from 155, so I'll go to 160. So now I'm allowing 15.5 MeV through, which is already higher than what the accelerator is producing. Our dose rate has increased a little bit, but any further increases in bending magnet are going to decrease the dose rate because we're now allowing the bending magnet wants too high an energy compared to what the accelerator is producing. So this is a different way of adjusting the accelerator beam energy from before. So we can adjust it now by adjusting the amount of electrons in the accelerator, and if by varying the accelerator current, we can vary the accelerator energy because of the fixed amount of RF power that's going into the accelerator, and which then has to be shared between different amounts of electrons. So this completes the last lecture on energy variation within an accelerator. And in the next lecture is what we're going to look at are how we adjust the accelerator now in order to produce different energy beams and what that does to the clinical properties of the beam.